So I was asked to talk about the non-magnetized masers, which are sort of a bit discriminated against, as you can see from the title that was given, the other masers. Okay, so I'll talk about the other masers. But before talking about the masers, I want to make the point that I believe that confidently identifying, do we have a pointer?
You have to use the stick.
The stick, okay, stick is good. So I want to first emphasize that I believe that confidently identifying the FRB production mechanism is quite unlikely in my view, for several reasons. One, we have a huge uncertainty in the plasma parameters that are relevant for the problem that we are discussing, orders of magnitude. And this is partly related to the fact that the radio emission may carry only a tiny fraction of the total energy involved in the events, like we know is the case for the repeater of 121102, which may or may not be representative. And the relevant plasma physics is complicated, it's nonlinear, it's multi-scale on very, very wide range of scales. So due to all these reasons, I think it's going to be quite difficult to pinpoint what the correct emission mechanism is. And probably the constraints on the progenitors will be obtained by other means, by localizations, by constraining the environments, and possibly finding counterparts. Okay. So nevertheless, since I was asked to talk about the masers, I'll talk about them. Collisionless shocks may produce unstable plasma particle distributions, which may relax to thermal distributions by emitting coherently emitting electromagnetic waves, which may produce FRB. The maser shocks that were discussed so far are of the magnetized type. Essentially, we have a highly magnetized upstream that flows into the shock wave. All the electrons are coming into the shock wave with a given momentum, and they are roughly reflected by the magnetic field. You have a very narrow angular distribution in momentum space. This is unstable and leads to possibly cyclotron emission. Oops, something is wrong.
Someone is joining us on Zoom. Can you please mute your microphone?
Yes, Roger. Okay. Now, a different type of possible maser emission is the one that I will be discussing, is in a non-magnetized collisionless shock. The idea is that as the fast upstream plasma approaches the shock wave, instabilities, like the Weibel instabilities, rapidly isotropize the particle distribution, but it is non-thermal. And a non-thermal particle distribution is unstable and could lead to a coherent emission. And this is indeed the case if the particle distribution is rising faster than thermal, so faster than gamma squared, the momentum squared, the distribution is unstable and leads to the emission of electromagnetic waves. It was known for a long time that in a situation where the ratio of the plasma frequency to the cyclotron frequency, these are low magnetization waves. If it's much larger than the characteristic electron Lorentz factor, then instabilities arise at the Racine frequency, which is given by the plasma frequency times the Lorentz factor of the electrons. We have shown that you can also obtain instabilities in the cases which are more relevant for us, where the electron Lorentz factor is much larger than the ratio of the plasma to cyclotron frequency, which is roughly the square root of the energy density ratio of the electrons in the magnetic field. And then the instability arises at the modified Racine frequency, which is the plasma frequency times the ratio of these plasma and cyclotron frequencies, which is the quarter root of the ratio of the energy densities in electrons and magnetic field. This is a result of the calculation of the negative reabsorption that arises in such a situation using the Einstein coefficient methods. In principle, we get strong negative reabsorption, so strong instability and amplification of the electromagnetic waves at the frequency just below this modified Racine frequency. Now, together with Andre, we've actually solved directly the dispersion equation for these instabilities and obtained generally a similar result to the one that is obtained by the Einstein coefficient method. And Andre has also done some approximate peak calculations of the instability that arises when you have an isotropic but non-thermal plasma distribution of particles like this. And we found that there's a wide range of instabilities that grow. The Langmuir waves grow faster than the Maser waves, but a significant fraction of the energy is converted to electromagnetic emission through this instability. For those of you who are interested in the plasma physics, I will make one comment that there is one interesting difference between the exact calculation and this Einstein coefficient standard method for calculating the instabilities, which is that for inclined propagation, the growth rates of the two circularly polarized modes are quite different, while in the Einstein approximation method, Einstein coefficient approximation method, they're going to have the same growth rate roughly. Okay, but this is sort of it's an interesting detail, but not crucial for our discussion here. So what is a possible mechanism for producing a fast Strauss-Weber burst using this type of instability? Well, let us consider a compact object that emits a highly relativistic shell of matter with some energy E and Lorentz factor gamma, and this shell propagates into some plasma surrounding the source with a characteristic density n. So as the ejected shell propagates through the surrounding medium, it drives a forward shock into the medium, heating it up, and a reverse shock is driven back into the ejecta, heating up the ejecta material itself. Okay? When this reverse shock crosses the ejecta, most of the energy is now carried by internal energy of the shock-heated plasma, and it is available for being radiated away. In principle, this model has three parameters: the energy of the shell, the Lorentz factor of the shell, and the number density into which it propagates. For the FRB, we have three observables: the radio energy emitted, the frequency, the characteristic frequency, and the duration. So you have three observables and three parameters. You can fit it, no problem. So if you want to be a bit more challenging, since we have found that a significant fraction of the energy of the shock can be converted to radiation, let us assume that indeed the radio emission is a significant fraction of the kinetic energy, so let's say about 1%. This sets the energy. And then let us also take the density in the upstream medium to be the density that we inferred from the persistent radio emission of this repeater 121102, which again may or may not be characteristic. Okay, now if we set these two parameters, we have one parameter left, the Lorentz factor, that should explain both the frequency and the duration of the burst. So the model, this model now is over-constrained. Now, if we take, for example, the Lorentz factor to produce the observed duration, so the Lorentz factor would need to be 1,000 to get a duration of 0.1 millisecond. And this sets the frequency of the emitted radio waves from the reverse shock. Okay, so the emission here is from the reverse shock. And this comes out to be a fraction of a gigahertz with rather weak dependence on the parameters of the emission. And there is an additional important constraint that should be satisfied, which is that the the propagating waves should be significantly amplified as they try to escape the plasma. Otherwise, you don't get a lot of energy out. So the negative reabsorption times the thickness is a few hundred, which implies that you get a very large amplification of the waves. So to summarize this point, if we have shells of energy which is not very much above the emitted radio wave energy, 10 to the 41 ergs or so, emitted at high Lorentz factor, about 1,000, from a compact object, and propagating into a density which is about 0.1 per cubic centimeter as we observe in 121102, then the reverse shock that is propagating backward into the ejecta may emit an FRB at the gigahertz with a fraction of a millisecond duration. Okay. However, we need to remember that the dynamics of the model is completely ad hoc. So we choose the energy and we choose the Lorentz factor. We don't know why the source emits a shell with this energy and this Lorentz factor. We have to postulate it in order to get the emission. Now, in the remaining few minutes, I want to compare this to the cyclotron or synchrotron maser that were discussed so far. So this is the cyclosynchrotron maser that was discussed up to now. Same thing, essentially. You have a fast shell emitted by the source, propagating into some upstream medium. There are two main differences between this model and the one that I've just described. Well, maybe not the model, between this scenario and the scenario that I've described. Here, the upstream plasma is assumed to be highly magnetized, and the emission is considered to be produced by the forward shock and not by the reverse shock. Okay? Now, this model has 4 or 5 parameters, depending how you choose. So in addition to the energy, Lorentz factor, density, you have the magnetization of the upstream, and also the ratio of the radiated energy and the shell energy. If you know how to calculate this from the other parameters, then you have only 4 parameters. But now you have 3 observables and 4 parameters. Of course, you can fit anything, and you can even have some interesting degeneracies between the models, as you can see here. So there are actually quite different types of magnetized magnetar models for the FRBs. The original models were discussing very highly magnetized with a very low electron-positron loading upstream wind, which are shock-heated by this some ejection from the compact object. Then there are models where the upstream plasma is highly loaded with electron-positrons, and the models that were discussed by Ben and Lorenzo just now have an upstream plasma which is an ion electron plasma with very high density. So these are quite different models, okay, or quite different scenarios. And just to just demonstrate that they are really different, you can look at the different densities that are assumed in the upstream in these cases. So they vary by 10 orders of magnitude between the first and the last model, okay? So these are not the same model. When you say a magnetar model, you need to explain what you mean. So it could be this, could be that, could be something else. But this is really a good demonstration of the fact that we have very little constraints on the plasma parameters of this problem. And in principle, we can get very different emission mechanisms to explain what we see. We have enough free parameters, and we have wide uncertainty in the parameters of the model. So there could be a wide range of physical mechanisms responsible for FRB emission. Maybe different systems operate in different regimes, and there are different mechanisms. Maybe there's one mechanism, with one characteristic set of parameters. I don't know. The other implication of this is that it's going to be very difficult to argue that we will constrain the parameters of the source from building models for the FRB emission. Okay, if we can change by 10 orders of magnitude the density, obviously we cannot constrain the density from these models. Okay. What? Yeah, usually, so I've shown here 3 models. Typically, the proponents of these models rule out the others, and vice versa, but okay, I don't want to get into that. Okay, to summarize, okay, there are at least 2 different types of maser mechanisms that can operate in collisionless shocks. One is the magnetized cyclotron-synchrotron maser that was discussed extensively. I would say that one of the sort of common prediction of these models, although they're quite different, is that only a tiny fraction of the energy comes out in the radio. And in this case, the burst should be accompanied by very bright X-ray, gamma ray, or optical emission, depending on the model. So where most of the energy comes out depends on the details of the model, but there should be accompanied by a very large, very strong emission in other wavelengths. And there is the other type, the other maser, which are the non-magnetized ones, where the efficiency may be higher. And most of the energy is, a significant fraction of the energy is emitted in the radio. And then we should see a rather weak accompanying emission in gamma rays, but the energy here is going to be similar to the radio energy, so it might be difficult to detect. Now, both models assume and do not derive the dynamics of the engine. Because you assume that there is a source that emits some energy with some Lorentz factor, and it's surrounded by some density and so on. All these parameters are ad hoc, put in by hand. They are not calculated. And both also lack basic principles calculations of the plasma instabilities. So, since we have orders of magnitude uncertainty in the plasma parameters, as I emphasized, there could be a wide range of possible mechanisms responsible for FRB emission, and it's unlikely that we will be able to pinpoint the correct one. And for the same reason, it's unlikely that we will be able to determine the source properties based on deriving an FRB mechanism. Some progress could be made if we are able to constrain the plasma parameters, like Lou's talk. Okay, if we can measure the density of the surrounding plasma because of some nonlinear effects, this would narrow down the uncertainty in the parameter space, and then we may make some progress. But still, I think real progress is most likely to come from localizations, environment, and counterparts. Okay, I'll stop here.